So welcome to the second video in the course ST1 on hypothesis testing. We're talking about t-tests and paired t-tests. So in the previous video, we discussed this idea about how we want to test for variation in data using this formula if we have all the samples in our population. So we can compare a single value x and look at the extent to which it is different from the population mean mu relative to the standard deviation s. We also looked at how we can look at sample sizes and compare our sample mean, x bar, against mu, adjusted for the standard error, which is the standard deviation divided by the square root of n. Well, in this part, we're going to look further at where we have instances of smaller sample sizes. For smaller sample sizes, say, and less than 30, what we can do is use a t-distribution instead of a normal distribution, and a t-distribution approximates a normal distribution depending on this sample size. So it's a family of distributions, each of which has a different sample size. And as you increase the sample size, the t-distribution increasingly approximates the normal distribution. So consequently, this formula effectively becomes the same as the z-distribution formula if we have sufficient sample sizes. So the t-distribution, in effect, adjusts for the uncertainty associated with fewer samples, and thus gives us a better estimate of the scale difference between the sample mean and the population mean. So what we can think about before is that we are doing a bunch of different experiments, and we're looking at the sample standard deviation, and we're assuming that that approximates the population standard deviation. And then if we have many samples, we can kind of apply this Z formula because we have this shape of the distribution. It's a Gaussian bell-shaped curve, and t-distribution is similar, but not quite the same. And what we're doing for this test is effectively looking to see the extent to which our sample mean compares to our global mean here. And what we have to consider is that if we have a smaller sample size, as illustrated by the graph in the previous video, we may have a poor estimate of our sample standard deviation as well as the other features. And for that reason, we use this shape of a distribution where the edges are slightly wider and the height here is slightly taller. And thus it has a slightly different distribution of p-values and percentiles as we move across this distribution for the same values. So t equals 2 on -2, if we have high sample sizes, will approximate a Z distribution, but if we have small sample sizes, it will be a little bit different. And what we want to do with our studio in the demonstration videos is get the two-tailed p-value, so we're getting the sum of the areas under the curve in the red on either side here because our distribution is symmetrical. So what we want to do is calculate the area going from -infinity up to this point, as highlighted here, or alternatively get the sum of the area going from +infinity down to this point. So slightly different calculations for each of these. So what we can say is that we're looking at a null hypothesis where we're assuming that we have some mean, say maybe it's a standardized mean where mu is equal to 0. We have our standard deviation, which is scaled to being the variance that both are 1. And then we have our some sample size. And we're trying to see, given this t-distribution, to see if our sample mean is close to our population mean relative to the standard error. So that's our kind of hypothesis, that the sample mean is within some distance away from the population mean. And our alternative is that it's actually different, that there's two different underlying populations here. So what we can do is look at this for different sample sizes and the shapes of the different t-distributions. And what you can see here on this diagram as we go right is the change for going from dark blue, which is n equals 3. So you can see there it's wider down here and smaller here and wider on this side because it's symmetrical. And then as you go up to n equals 10, you can see that it gets taller here and increasingly approximates the normal distribution and gets narrow down here. So that affects the uncertainty. So if you calculate the corresponding p-values for these different sample sizes, you'll find that they're different. We'll also have to do a calculation of the degrees of freedom, which we'll talk about later. But what's important to think about, if we're looking at the areas on the curve here corresponding to about 2 or thereabouts, what corresponding areas are under the curve for each of these? And they're different. You can see that they're all different. So we can calculate these ones and zoom in to that area under the curve. So let's say if we have a t-value of 3 there, you can see for the normal distribution is quite small. For n equals 20, it's bigger. For n equals 10, it's bigger again. For n equals 5, it's substantially bigger. Same for n equals 4 and n equals 3, and so on. So they're all slightly different. So this is our p-value threshold here. So you can see that they're all different. So the p-value for n equals 20 is going to be small for the t-distribution, and that is a corresponding degrees of freedom, and that corresponds to a p-value. So that would be, for 1.98, that would be 0.06, whereas for n equals 10, the same t-value has a different p-value of 0.7077, and the same t-value for n equals 5 is smaller, therefore the p-value will be bigger. There's more uncertainty, it's 0.12, and then if we've increased the sample size down up to 50, it'd be 0.05. So that's a consideration for this. We have to consider the sample sizes, and that's why the t-distribution is more accurate when we have a specific sample size we want to measure. So what features we want from our population to test this, and what RStudio will take in, is certain things. So you might have two different groups. I want to test the idea that the feature of interest, like height or whatever, of these distributions are the same. And we're assuming that the variances here are comparable. That's something that also needs to be considered. The sample sizes are reasonably large and comparable. So you might have the hypothesis that the difference in means is around 0 within acceptable boundaries based on the biological context of our experiment. And the alternative is that they are different or biologically different. So you have the mean and standard deviation of the first group, as well as the sample size and the same features of the other group. And that mean we can calculate our Z formula using these features. So essentially what we're doing is, sorry, our T formula is we're getting the mean of the first group minus the mean of the other group divided by the pooled standard error of X and Y together. So we're mixing the standard error. So in that sense, it's comparable to our Z formula where we have some value, some mean, X bar minus mu over the standard error as well. So this student t-test arose by the Guinness chief brewer, William C.D. Gossett, who developed these in the early 1900s in a few different papers, and hence this originated t-test comparisons between the differences in means between different groups is known as student's t-test. The one we actually use in R is typically Welch's t-test. So we'll look at how those are slightly different later in the RStudio demonstration lab. So we're trying to think about here is our transition from looking at the comparison of a reference value. So you might have some reference value here that we're comparing to our global mean, and we're looking at the area under the curve. We're going to move from doing one sample t-test to doing here a two sample t-test. So here we have X and Y. They're two different distributions, hypothetically, and they each have different variances and different sample sizes, M and N. And what we're trying to see is if there are underlying differences in their means relative to the standard deviation and sample sizes are actually different or not. So what can be useful for these tests is actually visualize these on pen and paper or with R to look at to what extent they overlap, and that can tell us more about how different they truly are. So the t-distribution gives us a sense of the difference between the groups. It doesn't tell us about the underlying features in this. In that sense, it's kind of a bias test because it's telling about the differences, not the actual means themselves. Another way of quantifying this is Cohen's d. So you might see that a lot. That's similar to a correlation coefficient in some way, Cohen's d. I guess that gives us the sales difference between the groups in similar to a t value. So t value and a d value, just like a z value, cannot be compared, but they're slightly different distributions, even an r value in the same way. They're slightly different distributions and therefore different p-values associated with them when we're looking at the differences. But that can be this kind of scaled difference, just like a correlation coefficient goes typically from 0 to +1 and down to -1. The d value is the same distribution centered on 0, and that can be more positive or more negative depending on what's being examined. So an example of a big biological difference is the heights between men and women. So if we look at that across different populations, you may get estimates of the order of d equals 1.7 to give you an illustration. But that's quite a big effect. And most effects that we actually look at will be smaller than that. And it's the question then, it depends on your experiment as to whether that is actually biologically of interest in your context of your work. Whereas the calculation of p-values, as we know, depends on the hypothesis being tested, the model being applied, which is the t-test one here, and how extreme you would expect data to be in the context of your experiment. So looking at this, we're looking at the t-value here rather than d-value. And what we're going to calculate is this formula here. So we're taking the mean of x, the mean of y, and calculating this, that we've got the standard deviation of x squared, the standard deviation of y squared divided by the sample size of x and sample size of y, m. So this is the standard error, and this is the difference in means that we have here. So that's our t value. So that's why the sample sizes may have an effect here, depending on what we calculate. So if we have different sample sizes, this means that the t value will be different. And because these are denominator here, they will have a kind of impact on the t value. And in effect, if we have smaller sample sizes, because it's a denominator, it will make the t value to be scaled in a different manner. In practice, students' t-test has a different formula for calculating the degrees of freedom. For Welch's t-test, we actually use this one. So it's somewhat complex to do by hand, but it's what is actually applied in practice by Welch's t-test. So let's look at the sum of the variances for each of the groups, scaled by the sample size, and then it's looking at 1 over n minus 1 and 1 minus n minus 1 of the other group as a denominator. So this approximates n plus n minus 2, which is a simple approximation of what the maximum degrees of freedom would be. However, we'll typically find that this formula for certain data sets is less than that, because if we have a data set where we have the same values over and over again, so let's say we have a data set where we get 10, 10, 10, 10 many times, that will reduce the amount of the standard deviation that this data set has, and thus gives a smaller degrees of freedom. Whereas if all the data points are very, very different, we'll find that the degrees of freedom then, even if we have the same sample sizes, will be larger. And that's important to note. So that's why when we do Welch's t-test for the same sample sizes, we actually find the degrees of freedom can vary a bit. So this approximation is handy for just a mental concept, and that represents the maximum one to compare for Welch's t-test. So that's the one you might use for students' t-test. So there's a few assumptions here. Firstly, that the variances of x and y are comparable. So if you compare the variance of x and y and look at their ratios, that can be one way of telling how different they are, and we'll apply that later for f-stats for what's known as Levene's test, which is simply the ratio of the variances. We assume that the sample sizes are comparable, and we also assume that x and y should be uncorrelated. So that's quite important, that if they're correlated, that might lead to differences that are affected by some other factor. So we might have x affecting y, and then other biological features like Z also affecting x and y as well. So we have to be careful about what specifically we're testing. In practice, we might have a kind of a one sample t-test like this. I think it's one sample. So if expected concentration of protein is 65, the alternative is that is greater than the 65. So that's a one-tailed test. Whereas for one-tailed p-value, given a threshold of 0.05, assuming that they're normally distributed. And we have this sample, so we have 2, 4, 6, 8, 10 samples. So we have n equals 10. So therefore, we get that corresponding t-distribution for n equals 10. So we're looking at a formula of looking at the mean of this set, whatever it might be, let's say 66.5 minus 65 divided by the variance of this set squared. So standard deviation squared over the sample size 10 here. So that's our formula. If we look then on the next page, what that would be, yeah, we got 65 minus 67. So that's our sample mean there, 67. So we're over here on the right-hand side. And then we have the sample variance, 3.2 here divided by the square root of 10. And that's our t-value we get at the end. So once you have that t-value, our studio will give us a corresponding p-value with that, but it's specific to that particular distribution. And this says here that for p-value threshold of 0.05, we need a t greater than 1.833. So that means our percentile here is actually smaller, it's about 0.04. So that's the 4th percentile, roughly speaking. And then for that means that the 5th percentile is something here, the 3rd percentile might be down here, and so on. If we calculate the degrees of freedom for this simple one sample t-test, it's simply n minus m because we have only one sample here. Sorry, n minus 1 because we have only one sample here. So that corresponds to the t-distribution that we look up. That is 9 degrees of freedom. If we move on from this is a 1 sample t-test to a 2 sample t-test, we can look at an instance where you have some protein A with a data set X, and then we have sample Y. So we've got 2, 4, 6, 8, 10 again. And let's count the other one, 2, 4, 6, 8, 8, 10. We've got 10 versus 10. So this formula now is different. We're going to have a X bar minus Y bar divided by the full standard error here. So you've got the standard deviation of X squared over N plus the standard deviation of Y squared over Y. So that means we have to get the mean of X, mean of Y, standard deviation of X, standard deviation of Y, and then it's over the root 10. So it's going to be something like this. And if we're getting the degrees of freedom, importantly, that's going to be, that can be approximated by n plus m minus 2, which in this case is going to be 18. So that's the corresponding t-distribution that we want to look up. So here we could hypothetically draw these different groups depending on what means we have. So I think we can see there that for the second group Y, it's a bit smaller. So if we draw Y, we'd find that it's a bit smaller than X. So my pen is working better today. So this mean is about 61.8 x 8 for Y. And this mean for X is 66.8. And therefore we're trying to see how different they are in that t-value. So we're looking at 66.8 minus 61.8. And then we need to get our values for the denominator. So it's 11.5 plus a 3.7 all over 10. And we're able to work this out as t equals 1.62. Now, if we look up our p-value for studio or log tables, if we're looking at that, we'll find that this is quite small. So there is a moderate difference, but it certainly has a percentile of the order maybe 0.09 or thereabouts. And what we can see straight away is that because the t-value here is less than 2, it's likely that our p-value is going to be greater than 0.06 at least. That gives us a sense of the percentile difference between these different groups. if we look at it in practice, we'll be able to work that out with our studio. If we look at another example, so here we have X and Y again, same approach. So let's just count the numbers. We have 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12. I think it's 12. Yes, it is. We've got the same formula. So we just have to get the mean of X and the mean of Y in our two-sample t-test. And we just have to bear in mind that you've got the standard deviation of X squared here over 10 minus the standard deviation of Y squared over 12 here. And we're able to look at the distributions once we get the means and the standard deviations. So that will be our first step. So you can see there X is a bit less than Y. So if we plot the distributions with my bad drawing, the mean of X is about 6.3. And the mean of Y here is about 10. And then the variance of X is 4.5. So that gives us a sense of the standard deviation. So you're talking about two standard deviations. Here is about 4, give or take. And here's 8. And then for Y versus 4, so that's going to be, about the same on either side. So you can see that there's a moderate difference, but the question is how extreme is it? So we can get our calculation then is 6.3 minus 10 divided by the square root of 4.46 over 10 plus 4 over 12. So you can see with a bigger sample size here, we actually might find that our t-value is slightly bigger as a consequence. So in this case, we find that our t-value is actually minus 4.4. So you know straight away that that is quite extreme, and slightly that our percentile will be less than 0.01. So this would suggest that in this case that we do not accept the null hypothesis, that they're the same groups. Whereas in the previous example, we would have accepted the null hypothesis, and therefore we can use our studio to get the exact p-value here, which is hard to do by hand. I note that the distribution we're looking at is going to be, the degrees of freedom will be, if we're looking using log tables, n plus m minus 2, which is t-distribution with 20 degrees of freedom. So you can see as degrees of freedom gets higher, then we have a better approximation of the normal distribution based on the t-distribution. Another type of t-test, moving from a one-sample t-test to a two-sample t-test, is a paired t-test. So we have right. That's the one we had. Yeah, if we do this with RStudio, we get the degrees of freedom is actually 11.43 instead of 20 because of these repeated values. You see 12 there multiple times. We see 7, 7, 7, 4, 4, for example, as well as 8 and 7, 8 and 7. So yeah, paired t-tests. So paired t-tests are different again. We have pre and post. Pre and post means that we're looking at the differences. So we cannot use a Welch's t-test or student t-test for these. We're looking at the differences before and after because they're correlated with each other. So if we plot pre versus post, obviously they're going to be somewhat correlated with each other. That's what we would expect. And to adjust for that difference, we have to look at the differences between them. So essentially we take post minus pre as our single set of values. So if this is our distribution of pre and post, we're looking at the differences. So maybe they all decline in some manner. So shown in the diagrams here, these differences of value of 1 there for the first one is what we take, not the value of 12. And thus our differences will be actually smaller compared to the original values. So you get the differences here, you get their standard deviation, and the standard error as well. And the formula is this: we got the mean of the difference, and we divide by the standard error. So it's a bit like the formula we had before. This is the standard error here on the bottom of our sample size, standard deviation there. That's the standard deviation of the differences too. So we're not using this formula in this case. That using that two sample formula is incorrect. So we could look at some examples here. So what we're going to do is basically get the differences for our pre and post values. So for our pre and post values here, we just can't calculate the differences. We have plus 2, plus 2, plus 2, and plus 5. Those are the differences, and we just sum them up. So you get the sum is going to be 11 divided by the number that we have, which is 4. So we get 2.75 as our mean difference. That's our mean difference here. In the same way, we get our variance as a standard deviation for that as well. So we're using this formula. D is equal to 2.75 divided by the standard deviation of D divided by the square root of n equals 4 in this instance. So what we get for the standard deviation in this instance would be 1.5. So 1.5 divided by 2, and that would give us a t value at the end of about 3.7. So you could say then that this difference, if we look at the values before and after, is probably going to be high. So you can sort of see that there. Initially, our mean, I think, is 2.5. Our post is higher, maybe 4, maybe 5. And we're seeing that they're different. Obviously, this is a simple example with just n equals 4 versus n equals 4 after, which is not very many. So that means we got a t distribution with degrees of freedom equals 3 that we're looking at. In practice, we might be comparing, say, 40 versus 40, which would be more robust than this simplistic example. In another example, we can look at this instance here. So we got plus 3, plus 2, minus 1, and then a big jump, plus 11 here. The same approach, we get the sum of these values, which is going to be, is that plus 11? Is going to be 15, I think. Scale before, so that's going to be 3.75 is our value for D. And then our T value, therefore, is going to be 3.75 over the standard deviation divided by 2. So that's going to work out as 3.75 over about 4.2 approximately for the standard deviation divided by 2. So therefore we get a t value that is large about 1.7. So with our t value with the degrees of freedom, t distribution with the degrees of freedom of 3, we can see that here the difference is probably going to be a percentile that is at least greater than 0.05 in this instance. So that kind of gives us an example of the key t-distributions that we're looking at. A 1 sample t-test, a 2 sample t-test that we can do with R, and then a paired t-test, and we can do that with R as well, and each are slightly different. So please see that demonstration for the hands-on application with RStudio.